Welcome to Lecture 4.4c. This unit's about applications of derivatives, and we're finally ready to move on to the second big category in optimizations. We've been talking about position graphs, and we're now going to move on to something called optimization. In this video, I'm going to show you how to use derivatives to set up optimization problems, and I'm going to give you an overview of the process for solving them, but we're going to focus mostly on the setup and then the kind of understanding the theory behind it. In the next two videos, we've got a lot more practice actually solving these problems. Let's start with understanding what optimization means. The word to optimize in the English language means to find the most desirable of a number of possibilities. So for example, let's suppose you love ice cream. You might ask the question, how much ice cream will optimize my happiness? When you ask that question, you're basically assuming that there's some ideal amount of ice cream. Too little ice cream and you won't have enough and you'll be sad. Too much ice cream, it'll make a mess on the floor and you'll also not be terribly happy. But somewhere in between, there's an ideal amount. To optimize your ice cream intake is to find that number that is the ideal amount. To think about a slightly more serious example, when a doctor writes a prescription, they have to think about what dose is going to maximize the health benefit to the patient while also minimizing the side effects. Too much medicine and the patient may just end up feeling worse because of the side effects. Too little medicine and it won't do any good. Finding that number in the middle is optimizing the amount of medicine they take. We use optimization in manufacturing and business all the time. In fact, one of the most common jobs for math majors who graduate college with a math degree is to do some version of optimization for some industry. For example, the car industry might ask the question, what's the least amount of metal needed to make a car that's still big enough for 4 people? Why would they want to ask this question? Well, if you think about it, the constraint big enough for 4 people is normal. They just have to produce a car that'll sell. But the least amount of metal is a desirable question for them because they want to try and reduce the materials they use because it's going to be cheaper for them. And as a business, they're always trying to reduce their costs so they can maximize the profit. When you see these red words, least, optimize, maximize, minimize, these are cluing you in to situations where we're trying to find an ideal amount. And these are kind of keywords, but this topic in general isn't a topic that you can do just by listening for keywords. You really need to understand this idea of a desirable amount, a greatest or least amount, and reading questions and identifying that idea is how you know it's an optimization problem. Sometimes we're just going to call them max-min problems because that's really what they are. Basically, there's 5 steps. Any word problem you do, you're going to start by reading and interpreting. And then the big step is where you write a function. Sometimes it's given to you, but usually you're going to have to come up with a function whose output is the thing you want to maximize or minimize. And coming up with that function in many of these problems is actually the hardest step. Everything else should be pretty easy. Once you have that function, you're going to identify any endpoints given the situation and the critical points. Remind me again, what are critical points? Exactly, critical points are numbers for x or for the input that make the derivative 0 or non-existent. And once you have endpoints and critical points, you're going to use the second derivative test to find the max or min. In some cases, maybe we'll use the first derivative test. Either one will work as long as you know how to determine, is this telling me a max or a min? Last step, which is really important, it's not just there as a matter of fact, is you need to interpret the max and min to make sure that you're actually answering the question that's asked. A lot of times the question is going to be some variation on just what is the max, and you need to make sure that your answer suits the way it was being asked. If you want to hear more about any of these steps, your textbook actually has a pretty good description on page 219, so look there. Here's the first example we'll talk about. Find 2 positive numbers whose product is 36 and whose sum is as small as possible. Now, this may seem like kind of a really unimportant problem. It doesn't feel very relevant to the real world. I get that. I do want to use this problem just because it's short, and I'm going to use it to show you an overview of the whole process for optimizing. The problems that are actually more interesting, a little more relevant to the world around us, tend to be a little bit longer. So we'll use this example and then another one that's pretty similar to look at the whole process, and then we'll talk about setting up some more relevant ones. When you set up a word problem like this, first thing is you want to make sure that you recognize why this is an optimization problem. Why is example 1 an optimization problem? Exactly. We're trying to make something as small as possible. And that's kind of cluing you into the fact that we're trying to minimize in this case. When you set up this problem, I'm going to recommend the normal word problem setup with one little thing added in. We always start with what we're trying to find, and that's just to make sure that your answer suits the way the question's asked. So in this case, we're asked to find 2 positive numbers. Now, the reason I've added goal into my setup is because 2 positive numbers doesn't really tell me enough to get started. And there's something else that we're trying to do here. When you read the question again, you'll realize we're trying to find 2 positive numbers whose sum is as small as possible. So really, my goal here is to find the numbers and to minimize their sum. And minimizing the sum is actually what makes this an optimizing problem. What are we given? Well, we're given that the product is 36, but what does that mean? Product's a keyword for multiplying. And so we're given that when we multiply these 2 numbers, we get 36. In order to write that down, I'm going to pick some variables. I'm going to let x and y represent my 2 numbers, and that makes it really easy to write down the given information, which is just that x times y equals 36. Okay, great. If you're following along, we've read and interpreted this problem. We understand what we're looking at. And our next big step is to set up a function whose output is the thing we're trying to optimize. In this case, we're trying to optimize the sum. We're trying to minimize it. So your work needs to start with writing a function. And the output of the function I'm going to label s, which stands for sum. And the input's going to be a variable. Now, right now, I don't know what variable it is, so I'm just going to leave that blank for a second. And we're going to start to work to put this function together. Well, let's start with what we know. First of all, we know that sum means addition. So the sum of the 2 numbers is basically just x plus y, the first number plus the second number. Now, this is not your actual function yet, because we have 2 different variables. Eventually, we're going to need to take the derivative of this function in order to find the critical points, but you can't take the derivative until you have only a single variable, which means I need to somehow get rid of x or y, and the way you're going to do this in almost all cases is by replacing one of the 2 with an expression that it's equal to, but an expression that uses the other variable. This should start to sound like Algebra 1 when you did systems of equations. In this case, I'm going to find my substitution by looking back at the given information. If x times y equal 36, and it has to because the function says so, then I know that y has to be the same thing as 36 divided by x. I just divided by x on both sides. Well, if y is the same thing as 36 over x, then x plus y is the same thing as x plus 36 over x. And just like that, we have a function with only one variable, a function whose output is the sum. The input x is one of the 2 positive numbers, and the output is the sum. This is the function that I'm going to base my optimization around. For this problem, I'm going to go through the rest of the process. For the rest of the examples in today's lecture, you're actually going to stop as soon as you have that function. Now, if you're following along in the steps, once we have the function, the next thing we want to do is check our endpoints and our critical points. Endpoints are restrictions on your x values. So for example, are there any rules about what x can or can't be? Well, there is a rule. It has to be positive, right? So there is a lower endpoint, and the lower endpoint is x equals 0. The numbers that we have to be bigger than 0 at least. This is actually an interesting endpoint though, because if you plug this endpoint back into the function, we actually get s of 0 does not exist. When we plug 0 into the function, we get a domain violation. So we don't actually have to worry about endpoints in this example. If you had endpoints that were not domain restrictions, what you would do is you would identify what the x values are, whether they're lowest or highest, and then you would plug those x values into your function and just keep track of the y values for future reference. You'll come back to them after finding the critical points. We're ready to find critical points now. So you probably remember from your winter break homework that critical points are where the first derivative equals 0 or the first derivative doesn't exist. What x values would make this first derivative not exist? Well, let's find the first derivative. To do that, I take the derivative of each term separately. The derivative of x is 1, and the derivative of 36 over x is negative 36 over x squared. Make sure you know why that's true. So I was asking what x values would make this non-existent? Well, 0. You're not allowed to plug in 0. But we've already seen that 0 is not in the domain of the original function, so we actually don't have to worry about that point, and we can discount that part of the definition. We do still need to set this equal to 0 and solve for x to find some other critical points. In order to solve for x, I'm first going to subtract 1 from both sides. And notice this is a rational function. It has the variable on the bottom. So to solve this, I'm going to set negative 1 over 1 and cross multiply, which brings me to x squared equals 36, which has two solutions, positive or negative 6. These are my critical values. Now that I have the critical values, in order to really find critical points, I want to plug each of these values back into the original equation. When I do that, I get y values or output values of 12 and negative 12. Now, it's going to be very tempting for you to say, oh, that must mean that 6 is the maximum because 12 is bigger than negative 12. Not so fast. It doesn't really work that way. You may have noticed that negative 6 can't be one of our numbers because we're supposed to have positive numbers. So we can actually discount this second one. But we still don't necessarily know that this one is the answer until we prove that this is a true minimum. We were trying to minimize the sum. If we accidentally found a maximum, then we really have a problem. So how can I prove that this point, 6, 12, is a minimum? This is where we're going to use either the first or the second derivative test. In this case, since I have the first derivative set up, we can go ahead and use the first derivative test. You want to start with a number line. And on your number line, you're going to mark the critical values and the endpoint values. So I marked 0 and 6. Even though we don't expect 0 to factor into our answer, it's worth noting there that we actually don't even care about what happens on this side. To do the first derivative test, I'm now going to plug in between numbers to my first derivative equation. Remember, the first derivative equation is this one right there. So a number in between 0 and 6 is like 1, for example. If I plug in 1, I get 1 plus negative 36, which is a negative number. And that means in between 0 and 6 right here, the derivative is negative, which means the original function is decreasing. If I plug in a number greater than 6, for example, 7, and put it up here, 7 squared is 49. Negative 36 over 49 is going to be a negative number that's less than 1, because the denominator is greater than the numerator. So if it's a negative number that's less than 1, when you add positive 1 to it, the whole answer is going to turn out to be positive. If you didn't follow the mental math there, you're welcome to use a calculator to double check that after 6, the derivative's positive. So that means at 6 itself, our function goes from decreasing to increasing, which means sure enough, this is a minimum value. Now, don't stop there. A ton of calculus students are going to stop there and are going to get the wrong answer because they forgot what we are actually supposed to be answering. Way back at the top, we started out by identifying that we're trying to identify two positive numbers. Well, I have two positive numbers here, 6 and 12, but that's not the answer because the two positive numbers are supposed to be the x and the y, the two numbers that multiply to 36. And 6 times 12 definitely doesn't equal 36. So let's make sure that we can interpret.